Have you ever wondered what brings those stunning visuals in your favorite video games and movies to life? The answer lies within those sleek, powerful components known as graphics cards. These unsung heroes render complex images and animations that captivate our imaginations. Join us as we explore the fascinating world of graphics cards and their impact on modern technology. From AAA games to computer-animated films, graphics cards are indispensable tools for creators and consumers alike. Their ability to process vast amounts of visual data has revolutionized entertainment, design, and scientific research. Buckle up and explore the world of GPUs, where silicon and software create breathtaking digital experiences. At the heart of every graphics card lies a sophisticated ecosystem of components working in perfect harmony to deliver stunning visuals. Think of a graphics card as a miniature computer within your computer, specifically designed to handle the demanding task of image processing. Its architecture is a marvel of engineering, optimized for parallel processing and high-speed data crunching. The journey begins with the Graphics Processing Unit, or GPU, the brain of the operation, which we'll explore in detail shortly. Working in tandem with the GPU is the Video Random Access Memory, or VRAM, a specialized type of memory that stores image data, textures, and other graphical information. This data is constantly accessed and manipulated by the GPU as it renders images, making VRAM a crucial factor in determining a graphics card's performance. Connecting the graphics card to the rest of your system is the motherboard interface, typically a high-speed PCIe slot. This connection allows the GPU to communicate with the CPU and other components, receiving instructions and exchanging data. Finally, the rendered images are transmitted to your monitor through a dedicated port, such as HDMI or DisplayPort, completing the visual pipeline. The Graphics Processing Unit, or GPU, is the beating heart of any graphics card, the engine that drives the visual experience. Unlike a general-purpose CPU, which is designed to handle a wide range of tasks, the GPU is a specialized microprocessor with a laser focus on graphics rendering. Its architecture is optimized for parallel processing, allowing it to perform millions, even billions of calculations simultaneously. Think of the GPU as a massive army of tiny processors, each capable of performing simple mathematical operations. These processors, known as shader cores, work in unison to tackle the complex calculations involved in transforming three-dimensional models, applying textures, and calculating lighting effects. The more shader cores a GPU has, the faster it can process visual data, resulting in smoother gameplay, faster rendering times, and higher frame rates. But the GPU's power goes beyond just raw processing muscle. It also incorporates specialized units dedicated to specific tasks, such as texture mapping, geometry processing, and pixel operations. These units work in concert with the shader cores, ensuring that every aspect of the rendering pipeline is handled with speed and efficiency. Imagine trying to access files on a hard drive while editing a video. The process would be excruciatingly slow. That's where VRAM comes in, acting as the GPU's dedicated high-speed memory, providing lightning-fast access to the vast amounts of data required for real-time graphics rendering. Without VRAM, the GPU would be starved for information, leading to performance bottlenecks and choppy visuals. VRAM stores everything from texture maps and frame buffers to vertex data and shader programs, ensuring that the GPU has all the resources it needs at its fingertips. The speed and capacity of VRAM play a crucial role in determining the level of detail and smoothness in games and other graphics-intensive applications. Think of VRAM as the GPU's personal warehouse, storing all the building blocks needed to construct the intricate visuals we see on our screens. The larger the VRAM capacity, the more information it can hold, allowing for higher resolution textures, larger game worlds, and more complex visual effects. Similarly, faster VRAM speeds ensure that data can be accessed and processed quickly, leading to smoother frame rates and a more responsive gaming experience. Section 5. The Cooling Conundrum. Keeping the graphics powerhouse in check. With great power comes great heat, and graphics cards, with their millions of transistors firing away at high speeds, are no exception. Effective cooling is paramount to ensure stable operation and prevent thermal throttling, which can significantly impact performance. That's why graphics cards come equipped with elaborate cooling solutions designed to dissipate heat and keep temperatures in check. The most common cooling method involves heat sinks and fans. Heat sinks, typically made of materials like copper or aluminum, are placed on top of the GPU and other hot components. These heat sinks absorb heat and transfer it away from the chip, where it's then dissipated by fans that blow cool air over the fins. For even more demanding scenarios, liquid cooling solutions can be employed. These systems use a closed loop filled with coolant that circulates through a water block attached to the GPU, absorbing heat and transferring it to a radiator, where it's then dissipated by fans. Liquid cooling offers superior thermal performance compared to air cooling, allowing for higher clock speeds and quieter operation. Section 6. From CPU to screen: a journey of pixels and processing power. The journey of a single pixel from its digital inception to its glorious display on your screen is a testament to the intricate collaboration between the CPU, GPU, and other components. It's a tale of data transformation, lightning-fast calculations, and synchronized communication, orchestrated by the invisible hand of software and hardware working in perfect harmony. The process begins with the CPU, which acts as the director of operations. It sends instructions to the GPU, outlining the scene to be rendered, the objects within it, their properties, and the desired lighting and effects. The GPU, armed with these instructions and the necessary data, gets to work, transforming abstract data into a visual feast for the eyes. The GPU's first task is to process the geometry of the scene, determining the position and shape of every object. It then applies textures, adding detail and realism to the surfaces. Next comes the lighting stage, where the GPU calculates how light interacts with the scene, creating shadows, reflections, and other visual effects. Finally, the rendered image is stored in a frame buffer within VRAM, ready to be sent to the monitor. Section 7. A world of GPUs, exploring different types and their prowess. Just like superheroes with unique powers, GPUs come in various shapes and sizes, each tailored to specific needs and performance levels. From integrated GPUs embedded within CPUs to behemoth dedicated graphics cards designed for extreme gaming, the world of GPUs is vast and diverse. Integrated GPUs, often found in laptops and budget-friendly desktops, share system RAM with the CPU, offering basic graphics capabilities for everyday tasks like web browsing, video playback, and casual gaming. While they lack the raw power of dedicated GPUs, integrated graphics have come a long way, with some models even capable of handling light gaming and creative workloads. Dedicated GPUs, on the other hand, are the heavy hitters of the graphics world. These standalone cards come equipped with their own dedicated VRAM and powerful processing units, delivering significantly higher performance for demanding tasks like AAA gaming, video editing, 3D rendering, and machine learning. Within the realm of dedicated GPUs, there are further distinctions. Reference cards adhere to the GPU manufacturer's standard design, while custom-designed cards offer modifications like enhanced cooling, higher clock speeds, and additional features like RGB lighting, catering to enthusiasts and overclockers. Section 8. Beyond gaming, GPUs as versatile powerhouses in diverse fields. While gaming might be the most prominent application of GPUs, their computational prowess extends far beyond the realm of entertainment. From accelerating scientific research to powering artificial intelligence, GPUs have become indispensable tools in a wide range of fields, driving innovation and pushing the boundaries of human knowledge. In scientific research, GPUs are used to simulate complex systems, analyze massive datasets, and accelerate drug discovery. Their parallel processing capabilities make them ideal for tackling computationally intensive tasks, such as protein folding simulations, climate modeling, and astrophysical research. In the medical field, GPUs are revolutionizing medical imaging, enabling faster and more accurate diagnoses. They power applications like CT scan reconstruction, MRI image processing, and real-time surgical simulations, assisting doctors in providing better patient care. The rise of artificial intelligence and deep learning has further fueled the demand for GPU computing. GPUs excel at the matrix multiplication operations that form the backbone of deep learning algorithms, enabling researchers to train complex neural networks and develop applications like image recognition, natural language processing, and self-driving cars. Embracing the future of visual computing. From simple display adapters to computational powerhouses, graphics cards shape our tech experiences. As we venture into the digital age, the demand for immersive visuals grows. GPUs lead this revolution, creating realistic games and life-saving tech. They process vast data, driving innovation in AI and VR, shaping the future of computing, transforming how we live, work, and play. Next time you marvel at stunning visuals, remember the graphics cards behind it all. Their story is a testament to human ingenuity and pushing digital boundaries.